Okay, today we're going to look at section 11.4, apportionment methods. So let's look a little closer at the apportionment problem. In the previous section, calculated the standard divisor and standard quotas in various apportionment scenarios. The results of those calculations routinely led to fractions and decimals of units. However, the seats in the House of Representatives, laptops in the classroom, or a variety of other resources are indivisible, meaning they cannot be divided up into fractional parts. This leaves a decision to be made. For example, if the standard quota for the number of laptops to be distributed to a classroom is 12.44 units, how do we deal with the fractional part of 0.44? It is unclear if the classroom should receive 12 units, 13 units, or some other value. So let's look at traditional rounding. The science department of a high school has received a grant for 34 laptops. They plan to apportion them among their 6 classrooms based on each classroom's student capacity. Use the standard quotas in the table below to answer each question. So we have a standard quota of 4.88, or standard divisor of 4.88. So using traditional rounding to determine the number of laptops assigned to each classroom. So with traditional rounding, 6.15 would be 6. B would be 5. C would round up to 6. D would round up to 7. E would round up to 5. And F would round up to 6. Find the sum. We have 6 plus 5 plus 6 plus 7 plus 5 plus 6, which equals 35. And does the sum found in part 2 equal the sum of the laptops available? No, so this method is not going to work initially. So the previous example demonstrates that we cannot successfully apportion indivisible resources by rounding off each standard quota using traditional rounding. This leaves us with a problem. What is a fair way to distribute the fractional part of the standard quotas? We will refer to this as the apportionment problem. Several methods for making this decision will be discussed, 4 to be exact. The reading coach at an elementary school has 13 gift cards to distribute to their 3 students as a reward for spending time reading. When they calculated the standard quota for each student based on the number of minutes the student had read, the results were 4.49 gift cards, 4.03 gift cards, and 4.48 gift cards. How does this demonstrate the apportionment problem? So since it is not possible to divide a gift card in traditional rounding will not work. This is an example of the apportionment problem. So we're unable to give somebody 4.49 gift cards. And looking at all these results, all of them would round down to 4, which would give us 12 gift cards with 1 left over. Now, the first method we're going to look at is called Hamilton's method of apportionment. One of the problems encountered when standard quotas are transformed into whole numbers using traditional rounding is that it is possible for the sum of the values to be greater than the number of seats available. The reasonable way to avoid this is to always round down, even when the first decimal place is 5 or greater. For example, a standard quota of 12.33 and a standard quota of 12.99 would both round down to 12. This is called the lower quota. The apportionment of 70 new emergency blue lights in 3 parking lots is based on acreage. The standard quota for each lot is listed in the table below. Use this information to answer each question. Give the lower quota. So for A, we have 30.88, so that would round down to 30. B, we have 18.53, which would round down to 18. And C, we have 20.59, which would round down to 20. Find the sum. Well, 30 plus 18 plus 20 is 68. How much does the sum fall short? Well, 70 minus 68 is 2. The standard quotas are all rounded down. Their sum will always be less than or equal to the house size. Then it would only remain to find a fair way to distribute the remaining seats. Alexander Hamilton, who was a general in the American Revolution, author of the Federalist Papers, and the first Secretary of the Treasury, took this approach to apportionment. So here are the 5 steps for Hamilton's method of apportionment. First, find a standard divisor. Then find each state's standard quota. Give each state the state's lower quota, with each state receiving at least 1. Give each remaining seat one at a time to the states with the largest fractional parts of their standard quotas until no seats remain. Check your solution by confirming the sum of the modified quotas equals the house size. Okay, so this example, this information we'll be using for all 4 methods. So, in our country of Imaginaria, there will be 4 states: Fictionville, Pretendstead, Illusionham, and Mythbury. Suppose there will be 35 seats in the legislature of Imaginaria. Use Hamilton's method of apportionment to determine the number of seats in each state based on the populations in the following table. So to find our standard divisor, we take the population, the total population, 1,593,000, divided by the number of seats, and that comes to roughly 45,514. Then, to find each state's standard quota, we divide the population by the standard divisor. And here I have 1.599, 5599, 1.5599, 2.5706, 4.6359, and 26.2335. Next, I find the lower quota. This would be 1, rounding down on everything, 2, 4, and 26. Next, I add the lower quotas. 1 plus 2 plus 4 plus 26 gives me 33. I need 35. So I need to add 2 more. So now we look at the decimal parts. The decimal parts. And we find a state that has the largest decimal part. That would be this 0.6359. So to this state, we add 1 and make it 5. And then we look for the next highest, which is 0.5706, and we add 1. So that's our 2 remaining. So this stays at 1, and this stays at 26, and when I add them up, I get 35. And I am done. The characteristic of an apportionment that is considered favorable is when the final quota values are all either result, or the final quota values all either result from rounding down or rounding up from the standard quota. The value that results from rounding down is called the lower quota. The value that results from rounding up is called the upper quota. As we explore more methods of apportionment, we will consider whether they satisfy the quota rule. If a scenario exists in which a particular apportionment allocates a value greater than the upper quota or less than the lower quota, then the apportionment violates the quota rule, and the apportionment method that was used violates the quota rule. So let's look at an apportionment method V has been used to allocate 125 seats to 10 states as shown in the table below. Determine whether the apportionment satisfies the quota rule and justify your answer. Okay, so looking at this gives us 11, which is the upper quota. We're good. Gives us 17, which is also the upper quota. We're still good. State D is 13, which is the lower quota, and I skipped state A. 42, which is the upper quota. State E is 18, which is the upper quota. State F is 4, which is less than the lower quota. And state G is the lower quota. So, method V does not meet the quota rule, because state F receives less than the lower quota. It is possible for an apportionment method to satisfy the quota rule in some scenarios but violate it in others. However, because the Hamilton method always begins with the lower quota and either adds 1 to it or keeps it the same, the final Hamilton quota will always consist of values that are either lower quota values or upper quota values. When the apportionment method has this characteristic, it is said to satisfy the quota rule, so we can say the Hamilton method of apportionment satisfies the quota rule. Although the Hamilton method of apportionment satisfies the quota rule, it can result in some unexpected outcomes, which has caused it to pass in and out of favor of the U.S. government over the years. There are several apportionment methods that have been popular alternatives, such as Jefferson's method of apportionment, that the founders of Imaginaria should consider. So another approach to dealing with fractional parts of standard quota is to modify the standard divisor so that the total of the resulting modified lower quotas is the necessary number of seats. This is the approach used by Jefferson. In Jefferson's method, the change to the standard divisor is made so that the total of the modified lower quotas equals the house size. The change in the standard divisor to get the modified divisor is relatively small. Unfortunately, there is not a formula for this. Modified divisor is found by guess and check. It is important to remember that increasing the divisor decreases the quotas, but decreasing the divisor increases the quotas. So if you need a larger quota, try reducing the divisor. If you need a smaller quota, try increasing the divisor. Suppose the population of a state is 12 and the standard divisor is 0.225. Find the state standard quota. So we simply take 12, divide it by 0.225, and that gives us 53.33. Now decrease the standard divisor by 0.2 units. So 0.225 minus 0.2 equals 0.025. Find the modified quota. 12 divided by 0.225, and this equals 480. Oops, not 225. 0.025 equals 480. Now increase the modified divisor from part 2 by 100, 0.100 units. So let's do that, and we get 0.125, and then determine the modified quota. 12 divided by 0.125 gives us 96. Choose any value of divisor between the value of the modified divisor from part 2, the value of the modified divisor from part 3. I'm going to use 0.100. Let's find my new quota, which is 120. Which modified quota was the smallest? The quota from part 2 or part 3? Part 3, because the divisor was largest. When you use Jefferson's method, you might have to adjust the divisor several times. Find modified lower quotas that sum to the house size. First, guess what the divisor should be based on the sum of the lower quotas, then increase or decrease it from there based on whether the sum needs to be smaller or larger, respectively. If the result still does not produce lower quotas that sum to the house size, adjust again and keep a record of the values that didn't work to help you narrow your search. So, steps for Jefferson's method of apportionment. First, we find the standard divisor. Then we find each state's quota. This will be the standard quota the first time step 2 is completed, and the standard divisor is used. But step 2 may be repeated as needed using modified divisors. Find the state's lower quotas, with each state receiving at least one seat, and their sum. If the sum from step 3 equals the number of seats, the apportionment is complete. If the sum of the lower quotas is less than the number of seats, reduce the divisor. If the sum of the lower quotas is greater than the number of seats, increase the standard divisor. Return to step 2 using the modified divisor. So again, we're back to Imaginarian, and it's 4 states. If you recall, the standard divisor worked out to be 45,514. Our standard quotas, 1.5599, 2.5706, 4.6359, and 26.2335. With my lower quotas, I had 1, 2, 4, 26, which came to 33. Now, it took me 5 trials to get this right. And the modified divisor I used was 42,500. So using that, here I get 1.6705, 2.7529, 4.9647, and 28.0941. This is 1, this is 2, this is 4, and this is 28, which brings me to 35. Note this. So notice that in this apportionment, Miss Berry received more than the upper quota. The lower quota is 26, the upper quota is 27, and it received 28. Since this apportionment of representatives to imaginary states by Jefferson methods does not satisfy the quota rule, we say Jefferson method violates the quota rule. Now we've discussed two apportionment methods, one that satisfies the quota rule and one that does not. Before you decide which method to use in Imaginaria, there are a couple more options to consider. Next, we look at Adams' method. Adams' method of apportionment is another method of apportionment that is based on a modified divisor. However, instead of basing the changes on the sum of the lower quotas as Jefferson did, Adams uses the upper quotas. To apply Adams' method of apportionment, there are 4 steps we follow. Find the standard divisor, find each state's quota. This will be standard quota the first time step 2 is completed and the standard divisor is used. The step 2 may be repeated as needed using modified divisors, resulting in modified quotas. Find the state's upper quotas and their sum. The sum from step 3 equals the number of seats the apportionment is complete. The sum of the upper quotas is less than the number of seats, reduce the standard divisor. The sum of the upper quotas is greater than the number of seats, increase the standard divisor. Turn to step 2. So let's do Adams using our Imaginaria 4 states. Recalling standard divisor of 4514 and standard quota 1.5599, 2.5706, 4.6359, and 26.2335. Recall, we're getting this by dividing the population by the standard divisor. Now we want the upper quotas. So this would be around 2, 3, 5, 27. Round up, no matter what. And that gives us 37. Okay? The sum of the upper quotas is less than the number of seats, reduce the standard divisor. If the sum of the upper quotas is greater than the number of seats, increase the standard divisor. So we need to increase our standard divisor. And again, this took several tries. And I ended up using 48,000. And that gave me my quota of 1.4791, 2.4375, 4.3958, and 24.875. Rounding up again, I get 2, 3, 5, 25. And that gives me 35. So this is correct. And again, look here. If the upper quota is 27, the lower quota is 26. However, we're assigning 25. In this apportionment, Miss Berry received less than the state's lower quota. So this apportionment is an example of a scenario in which Adams' method violates the quota rule. Adams' method of apportionment violates the quota rule. So far, only Hamilton's method satisfies the quota rule. There's one more method we're going to look at. The last method is Webster's. Webster's method of apportionment is another method of apportionment that is based on a modified divisor. However, instead of basing the changes on the sum of the lower quotas as Jefferson did, or the sum of the upper quotas as Adams did, Webster uses traditional rounding. So we follow the same steps. Find the standard divisor, find each state's quota, This will be the standard quota for the first time step 2 is completed and standard divisor is used. Step 2 may be repeated as needed with a modified divisor and modified quotas. Now, here's where it's different. Round each state's quota to the nearest whole number and find the sum of these values. If the sum of the rounded quotas equals the number of seats, the apportionment is complete. If the sum of the rounded quotas is less than the number of seats, reduce the divisor. The sum of the rounded quotas is greater than the number of seats, increase the divisor. Return to step 2 using a modified divisor. When using Webster's methods, just as with Jefferson's, the modified divisors you use may be different from what another person chooses. The final apportionment values will be the same. So again, here we are back to Imaginaria and its 4 states. And our standard divisor was 45514. And that gave me 1.5599, 2.5706, 4.6359, and 26.2335. Just to make a note, our lower quotas, 1, 2, 4, 26. Rounding, this becomes 2. This rounds up to 3. This rounds up to 5, and this rounds down to 26, which gives me 36. So I have one too many. Let's double check this. If the sum of rounded quotas is greater than the number of seats, increase the divisor. And again, the issue with these is it could take a long time. So I did this several times. And I used a spreadsheet to make it quicker with all the repeated division. I ended up using 46,820 as the modified divisor. This gives me my second set of quotas of 1.5164, 2.4989, 4.5066, and 25.5019. So rounding, this would round up to 2, this would round down to 2, this would round up to 5, this would round up to 26, and we would end up with 35. And there we go. So far we know that the Hamilton method satisfies the quota rule, while Jefferson and Adams methods do not. The apportionment in the example above is a scenario in which the Webster method satisfies the quota rule. Does it always? I have a little more work to do to find out. However, one thing is clear, not all apportionment methods have the same results. Before we make such an important decision for Imaginaria, it's important to think about the differences in the apportionments that result from these 4 methods. How will the differences affect the citizens of Imaginaria? So, comparing apportionment methods. Recall that the 4 apportionment methods discussed in this chapter differ in 2 ways: whether or not a modified divisor is used and the type of rounding of the quotas that is used. How might these differences affect Imaginarians? In the next 2 examples, we compare the results when different apportionment methods are applied to the same scenario. So, again, looking at the 4 different uses of our work in Imaginaria, which apportionment method would the citizens of the largest state likely favor? The largest state was Mississippi, and they would favor Jefferson's method because it gave them the most representatives. And their least favorite would be Adams and Webster. And that is because it gave them the least number of representatives. As a group, which apportionment method would the citizens of the other three states likely favor most and least? Well, most would be Adams and Webster's, because again, it gave them the most of the largest number of, and least would be Jefferson's. Adams' method favored the smaller states, and the Jefferson method favored the larger states in the previous example. But is this the case in general? Since Jefferson method begins with lower quotas, any adjustment to the quotas will be an increase. As you have seen, this is accomplished by using a modified divisor that is smaller than the standard divisor. The next example compares the impact of a decreasing divisor on, or the next example compares the impact of a decreasing divisor on the modified quotas of large states to the impact of the same size decrease on small states. The following table displays the effect of increasing the size of the divisor. Observe the effect this has on modified quotas of smaller states versus larger states, and use the table to answer each question. So we have A, B, and C, population of 10,000, 100,000, a million. Okay, so when the divisor increases from 11,100 or 11,500 to 12,000, how many representatives are lost by each? Well, A and B lose 0. This is going to be 1, and this is going to be 1. This is going to be 8, and this is going to be 8. However, C, this would be 86, and this would be 83. C loses 3. Now going from 1,200 to 12,000 to 12,500, this would still be 1, this would still be 8, and this would be 8, 80. So the answer is the same. A and B receives 0, lowers by 0, and C lowers by 3. And of course, which state loses the most representatives? State C. As we've seen, different apportionment methods can have the same results in some scenarios, but different results in others. Citizens of states which receive fewer seats with a particular apportionment method will view the apportionment method as flawed and argue in favor of a different method. This inevitably creates debates regarding the use of one method over another. Methods that favor larger states are likely to be challenged by smaller states. Methods that favor smaller states are likely to be challenged by larger states. And methods that violate the quota rule are likely to be challenged by states of any size, depending on the circumstances. So looking at the state of Hawaii House of Representatives, it has 51 representatives, each with their own district. Imagine that redistricting was underway and the representative districts were to be apportioned to each of the 5 counties based on population. This table shows the apportionment that would result from the use of Jefferson, Adams, Webster methods of apportionment. So from the table you can see that Hawaii and Oahu and Maui receive the same number of seats regardless. All sixes, all ones, all sevens. However, citizens of Honolulu would likely reject the Adams and Webster methods, arguing that they violate the quota rule. Lower quota is 35, they give 34. Similarly, citizens of Kauai would probably reject the Jefferson method based on the argument that it unfairly favors the larger states. This scenario demonstrates that the Adams and Webster methods violate the quota rule, but the Jefferson method also violates the quota rule at times. The Hamilton method is the only method that satisfies the quota rule in all scenarios. It is also consistently favors neither larger nor smaller states. Unfortunately, it can have some strange results in certain circumstances, which we'll see in the next section.